Bismillahirrahmanirrahim. I'm Amal Sohail and my roll number is 21TE04. Today I'm going to implement Lab 5 of Digital Signal Processing, which is about representation of discrete time digital signals into frequency domain. The objective of this lab is representation of discrete time digital signals into frequency domain, resolution of spectrum, computation of magnitude, phase, and power spectrum, spectrum leaking, and avoiding spectrum leaking. Task 1 of the lab is about DFT calculation. Discrete Fourier transform can be calculated by using the following formula, whereas inverse discrete Fourier transform can be calculated by using the formula below. So the task 1 is make your own functions myDFT and myIDFT for calculating discrete Fourier transform and its inverse using above given formulas. The provided arbitrary signals are as follows. Let us observe the code. The myDFT function calculates the discrete Fourier transform of an input signal x. It first determines the length of the input signal to establish the size of DFT, then it generates arrays representing time indices and frequency indices k for DFT calculation. Utilizing Euler's formula, it computes the twiddle factor Wn, a complex exponential term crucial in the DFT formula. Then it constructs the DFT matrix by raising the twiddle factor to the power of outer product of n and k. Finally, the DFT is computed by performing matrix multiplication between the input signal and DFT matrix, resulting in DFT coefficient stored in output variable capital X. The next function is of my inverse DFT, which computes the inverse discrete Fourier transform of an input signal, Fourier coefficients X. It begins by determining the length of the input coefficients to establish the size of IDFT. Then it generates the array representing time indices and frequency indices. Then it calculates the twiddle factor using the Euler's identity. Finally, it computes the IDFT by using the scaling factor 1 by n. In the calling section, this code performs discrete Fourier transform and inverse discrete Fourier transform operations on 4 input signals x1, x2, x3, and x4. First, it calculates a DFT of each input signal using myDFT function and stores the result in capital X1, capital X2, X3, and X4. Then, it calculates the inverse DFT function by using myIDFT function defined in the previous script. Now, by running this code, here we can see the output that prints the DFT results and the inverse sequences to the command window for inspection. This code demonstrates the functionality of custom DFT and IDFT functions by transforming signals into frequency domain and then back to the time domain, maintaining signal integrity. So here we can see the discrete Fourier transform of the above signals, whereas the inverse DFT represents the original signals converted back into time domain. Task 2 is frequency resolution can be enhanced by adding trailing zeros. Calculate DFT for following signals and observe the change in frequency spectrum. Let us observe the code. This MATLAB code calculates and plots discrete Fourier transform magnitude spectra for 11 different signals, each with varying lengths and zeros padding. It first defines 11 different signals ranging from simple sequences to zero padded sequences, and then computes a DFT for each signal using the FFT built-in function for discrete Fourier transform calculation. Subsequently, it plots the magnitude spectra of the DFT results for each signal using the stem function, arranging them in a 5x2 subplot grid. By running the code, here we can see each subplot represents the magnitude spectra of a specific signal with titles including the signal's length n and its corresponding index. This code facilitates the observation and comparison of frequency spectra for signals with different lengths and degrees of zero padding, illustrating the effect of zero padding on frequency resolution in the DFT domain. Task 3 of the lab is about the use of MATLAB built-in functions for an arbitrary signal. Let us observe the code. Here we can see the MATLAB code demonstrates fundamental operations related to the discrete Fourier transform and its inverse. Firstly, it computes the DFT of a given signal by using FFT, fast Fourier transform algorithm, storing the result in capital X. It then extracts the real and imaginary parts of the signal, then computing the magnitude and phase angle of each frequency component. The magnitude represents the amplitude of each frequency, while the phase includes the phase shift relative to the original signal. Finally, the code performs an inverse DFT on the frequency spectrum X to reconstruct the original signal in the time domain stored in XS. So by running the code, we can observe the discrete Fourier transform, its real and imaginary parts, and its magnitude and angle, and finally the original result, which is inverse discrete Fourier transform that is used to reconstruct the original signal, which is provided above, which is x is equals to 1, 2, 3, 4. The last task of this lab is to calculate DFT and plot magnitude spectrum, phase spectrum, and power spectrum for signals in task 2. Observe the effect of zeros padding. So what is zeros padding? It refers to the process of appending zeros to the end of a signal or data sequence to increase its length. This technique is commonly used in the context of discrete Fourier transform to enhance frequency resolution. When performing DFT, increasing the length of input signal by adding zeros at the end effectively interpolates more frequency samples in the frequency domain. So let us see the code. This MATLAB code defines a set of discrete signals, each with different lengths and zeros padding at the end. It then iterates over each signal to calculate its discrete Fourier transform using the fast Fourier transform algorithm. It then computes and plots three spectra, which are magnitude spectrum, phase spectrum, and power spectrum. For each signal, the code first pairs it with zeros to the next power of 2 to optimize FFT computation. The DFT of the padded signal is calculated and its magnitude spectrum represents the amplitudes of each frequency component. The phase spectrum represents the distribution of the phase angles of each frequency component, whereas the power spectrum illustrates the distribution of signal power across frequency bands. Now let us run the code. Here we can see that each spectrum is plotted in a separate subplot for visual inspection, with titles indicating the signal strength and the type of spectrum being displayed. Like the first subplot represents the magnitude spectrum of the specific arbitrary signal. The second subplot represents the phase spectrum, whereas the third subplot represents the power spectrum. This code facilitates the analysis and visualization of frequency characteristics for a variety of discrete signals with different lengths and degrees of zeros padding. So we can see that the 11 figures are generated because of the signal length, and each figure represents the three different spectrum analysis for specific arbitrary signals. Thank you so much for watching. See you in the next video. Allah Hafiz.